Networking hardware. About this module. Welcome to the networking hardware module. In this module, you'll be introduced to how computer networks form the complex web of connections that devices use to communicate with each other. You'll explore various types of networking hardware and learn how data flows over a network. You'll get an overview of how network hardware is placed and how IT support technicians play a supportive role during the network installation process and a primary role in the ongoing care and maintenance of network cabling. Finally, you'll learn how to troubleshoot network hardware and how to apply preventative maintenance techniques to keep networks running at their best. Learning objectives. After completing this module, you should be able to describe networking hardware components, types of networks, and types of network cables. Follow the process to place network hardware, place network cables and connectors, and upgrade a network. Apply troubleshooting techniques for network hardware issues given a scenario. About this lesson, Introduction to Networking Hardware. In this lesson, you'll learn about the basics of networking hardware and network types. You'll discover how each of the following functions in different types of networks: routers, switches, wireless access points, network interface cards, repeaters, bridges. The different types of networks include personal area networks, PANs, local area networks, LANs, wide area networks, WANs. You'll also learn about the types of network cables that enable data transmission across different distances and environments. Computer networks. In the digital age, our world is more connected than ever. The devices we use every day, from smartphones to computers, rely on a complex web of connections to communicate with each other and access information. Activities you do every day are part of networking. When you're watching a streaming video on a service such as YouTube or TikTok, have you ever thought about how the video makes its way through the internet to your phone, tablet, or laptop? You know that when you select a video online, you can instantly start watching it. And you know that thousands of other people can watch the same video at the same time. The process seems so simple that it's easy to take it for granted. But what makes it possible? When computers and network devices are connected to each other in a way that lets them share data and resources between each other, they form a computer network. A computer network is a group of computing devices that share data and resources. Take the example of watching a streaming video. When you watch a YouTube video, your device sends a request to YouTube's servers, and the server divides the video into small pieces called packets. These packets travel through networking hardware to your device, where your device reassembles them into the video you see on the screen. All the devices that enable and manage this process are part of the network. The network's role is to manage this process efficiently, ensuring smooth delivery. A network can be small, with only a few devices, such as a laptop and a router. Or it can be large, such as an office building full of desktops, laptops, connected servers, routers, and modems. These network devices are sometimes called network nodes or endpoints. The technologies that connect the devices might use physical wires, wireless electromagnetic signals, optical waves, or radio waves. Devices send, receive, and share data, such as streaming videos, using these networking technologies. Network resources include data, computing devices, and peripherals that you can access through network connections. Think of a network as a web of interconnected devices communicating with each other to enable the digital world you live and work in. Networking hardware. Page 1 of 2. Video transcript. Networking hardware. Welcome to the fast-paced world of Tech, where technology drives productivity and seamless communication. In this dynamic environment, the network infrastructure ensures that everyone stays connected and their devices run smoothly. Let's walk through the network hardware in this office, including routers, switches, wireless access points, network interface cards, repeaters, and bridges. First, routers and switches form the backbone of this office's connectivity. Routers guide data between different networks, ensuring that information finds its way to the right destination, whether it's within the office or across the globe. Switches connect devices like computers, printers, and servers, facilitating resource sharing and seamless communication. Wireless access points go beyond cables and wires, allowing the workforce to connect wireless devices to the network and be productive on the go. They act as digital beacons, guiding devices to join the network without the need for cables. A network interface card, or NIC, is like a digital translator for devices. Just as a translator assists individuals speaking different languages, NICs convert data from your computer into a format that can be transmitted over the network, and vice versa. These small yet powerful cards enable devices to communicate over the network, allowing the office to share, stream, and access information quickly. Repeaters play a vital role in extending the range of a wireless network. Think of them as network boosters, carrying signals further and stronger to cover every part of the EastoTech office. Bridges are clever connectors. They link two networks and facilitate data exchange. They are like digital traffic controllers, directing the flow of data between two networks, even if they speak different languages. The EastoTech network hardware uses two specific network types, a local area network, or LAN, and a wide area network, or WAN. LANs cover smaller areas, like the office premises, creating a tightly knit digital community where devices interact in close proximity. WANs, on the other hand, connect geographically dispersed sites, empowering collaboration across the globe. The most commonly used WAN is the Internet. Now, let's demystify how data flows through these interconnected devices. Data is like a traveler seeking its destination. It gets divided into small packets, each carrying a piece of the message. These packets journey through the network, hopping from one device to another, guided by routers, switches, and bridges. Page 2 of 2. Safeguarding the network infrastructure is critical, to prevent unauthorized access, data interception, and disruptive attacks, and that's where firewalls come into play. Firewalls are the virtual guards, protecting the network from malicious threats. And there you have it. With a well-designed network infrastructure and expert support, this office stays connected, productive, and ready to conquer any challenge. Networking hardware components. The web of interconnected devices requires physical hardware components working together. These components, collectively referred to as networking hardware, act like the traffic signals, on-ramps, and bridges of the digital world. Routers act as traffic signals, and switches act like traffic cops. Wireless access points provide on-ramps to connectivity, network interface cards act as interpreters, and repeaters are like gas stations. Bridges connect different segments of a network. Select each marker, plus, on the following graphic to learn more about how network hardware components function in a network environment. Router. Routers are fundamental in directing traffic between networks. A router connects different networks and ensures that data finds its way through interconnected networks. It serves as a map of the network, directing data to the correct addresses. Switch. Switches are fundamental in directing traffic within a network. A switch works within a single network and helps devices within that network communicate with each other. Think of a switch as a traffic cop, directing traffic within a busy intersection. Bridge. Bridges connect different segments of a network, functionally making these segments into a single network. They filter traffic, only allowing data to cross to the other side of the bridge if it's needed there. Picture a bridge over a river that links two land areas so they can function as one. In a network, a bridge serves a similar purpose, ensuring that information flows efficiently between two different network technologies and allowing them to function as a single network. Repeater. Repeaters are like gas stations that refuel a car so it can continue its trip. They amplify and repeat signals traveling across a network to extend the range. This ensures that data reaches all parts of the network without losing integrity or quality. Imagine shouting across a valley, and a friend in the middle repeats your message so other friends can hear it on the other side. That's what a repeater does for a network. Wireless access point. Wireless access points, WAPs, act as a gateway for devices to connect to a wired network wirelessly. They are like on-ramps that allow computers, smartphones, and other wireless devices to join the network without physical cables. When you are online in a coffee shop and connecting to their free Wi-Fi, you're using a wireless access point. Network Interface Card, NIC. Network Interface Cards, NICs, are bilingual translators that allow computers to understand the network's language and communicate with other devices. They can be internal as part of the computer's system board or externally connected through a USB port. Each of these network components plays a specific role in how data gets from one place on a network to other places securely and quickly. Next, you'll explore how these components enable data to flow over a network. How data flows over a network. To understand how each piece of hardware functions in a network environment, imagine a text message traveling from one device to another. The text message originates on the mobile device of one person and ends up on the mobile device of another person, or many other people. Take the following journey through network hardware with the text message and explore how the data that makes up the message moves from place to place. Beginning the adventure. Hello, I'm a text message, and I'm about to take you on a journey from one mobile device to another. Fasten your seatbelt. It's going to be an illuminating ride. My adventure begins when my sender presses the send button. I'm instantly transformed into digital data, and my journey through the network begins. First stop, the network interface card. An illustration of a text message with human facial features. Getting translated. I reach the NIC, where I'm translated into a language that the network understands. Now, I'm ready to explore the network. A postcard featuring an illustration of a text message with human features standing on a NIC card. The illustration reads, "Wish you were here." Taking the on-ramp. I move from the mobile device to a wireless access point, WAP. The WAP ensures I get on the right network without any delays. It's like using an on-ramp to get on the freeway. A postcard featuring an illustration of a text message with human features standing on a wireless access point next to a post office stamp. Navigating the path. The router is like a guiding map, helping me navigate the best route through different networks, while switches act like traffic cops, directing messages like me within the local network. They make sure I'm on the right path and moving efficiently. A postcard featuring an illustration of a text message with human features standing in a city by the water, next to a router and switches. Refueling. Sometimes, the journey gets long, and my signal starts to weaken. That's when the repeaters really help, like gas stations, increasing my energy so I can continue my trip without losing any strength. A postcard featuring an illustration of a text message with human features standing near a repeater in front of a gas station. Building connections. I encounter bridges that connect different segments of the network. They ensure I only travel where needed, making my journey more efficient. It's like taking a shortcut only I'm allowed to use. A postcard featuring an illustration of a text message with human features standing on a bridge. Arriving. Finally, I reach my destination, the receiver's mobile device. Through NICs, WAPs, routers, switches, repeaters, and bridges, I've made it intact to the recipient's device, ready to be read. It's been an exciting adventure. A postcard featuring a woman holding a cell phone and a text message with human features. Traveling through the network. I've traveled through a complex network of components, each playing a unique role in my journey. This story isn't just about me, A simple text message. It's a glimpse into the world of networking hardware that makes daily digital communication possible. Next time you send a text, remember the adventure it's about to embark on. Although the journey of a text message provides an engaging insight into the world of networking hardware, the actual data flow within a network involves intricate technical processes. Routers, switches, NICs, WAPs, repeaters, and bridges work in unison, following specific rules to ensure efficient communication. Understanding these hardware components is the foundation for exploring the broader landscape of network types. Next, you'll explore the various types of networks, including personal area networks, PANs, local area networks, LANs, and wide area networks, WANs. You'll discover how they differ in scope, function, and application. Types of networks. Networks facilitate the flow of information. They come in various configurations and sizes, each designed to meet specific needs and applications. The following three fundamental types of networks lay the groundwork for digital connectivity. Select each card to learn more about types of networks. Personal area network. PANs connect devices over a small physical area, such as within a single room. Local area network. LANs extend connectivity to a larger space, such as an office building or a campus, acting as the backbone of many organizational networks. Wide area network. WANs enable connectivity on a larger scale, connecting cities, countries, or even continents. The world's largest WAN is the Internet. Your personal network, send data between devices in proximity. Many modern devices allow you to pay for products by touching your device to a pad at the store. You also can send files and photos to a friend wirelessly if they're in the same place you are. You can do these things because of specific networking languages called protocols such as Bluetooth and Near Field Communication, NFC. Protocols are a set of rules and conventions that dictate how data is exchanged and transmitted across a network. They determine how devices on a network speak to each other, ensuring that the data sent from one device can be understood and processed by another. While numerous protocols exist, for now, let's focus on understanding the vital roles that Bluetooth and NFC play. A person tapping a mobile device with NFC technology to a point-of-sale device to pay in a store. In mobile devices, specialized hardware components, such as a Bluetooth transceiver and NFC chip, are responsible for enabling Bluetooth and NFC functionalities. Some devices, such as modern smartphones, have an integrated chip that combines multiple functionalities, including Bluetooth and NFC, into a single chip. For Bluetooth and NFC protocols, the networking technology depends on two devices being physically close together. You can't use NFC or Bluetooth to send data to someone in another town or even another block. Networks that enable communication within a limited range are called personal area networks, PANs. Their name is eponymous, the network only covers devices within reach of one person. Bluetooth and NFC protocols establish personal area networks. But a USB connection between a computer and a peripheral device such as a printer is also an example of a PAN. One benefit of personal area networks is security. In a PAN, regulated access gives you control over the transfer and reception of data. Whether you are sending a file from your phone to your tablet or connecting a wireless mouse to a computer, the network requires your explicit approval. This level of control, along with the limited nature of PANs, ensures data integrity. Because data can only travel between devices that are under your direct control, the PAN has a valuable layer of security. You decide which devices can communicate with one another. PANs are personal and secure. What do you think? Critical thinking. Because many modern devices and services are beginning to embrace PANs, support is growing. Aside from transferring payments at a store or sharing files and photos with a friend, can you think of other ways PANs can be useful? Evaluate your thinking. Does your answer account for the following? Another way PANs can be useful is for quick knowledge transfers. For example, a museum might use an NFC chip to provide additional details about a display to visitors who use their mobile phones. Another example is a docking station for your laptop that allows the use of multiple monitors, a mouse, keyboard, and printer. PANs are popular because they can be low cost, efficient, and portable. When you need a simple connection, a PAN can replace bulky cord connections. A home or business network, known computers can communicate freely. PANs are useful when you need to complete a particular task, such as printing a single file from a nearby printer. But most of the work that you perform on your devices involves streaming data, moving many files at a time, and receiving push notifications for news, weather, messaging, and similar activities. For this real-time functionality, you need a full-time connection to a larger network. When at school or a workplace, you might print a document from your laptop to the printer down the hall or share files between computers within the same building. Local area networks, LANs, make these tasks possible. LANs facilitate communication and resource sharing among devices in a specific location by connecting them wirelessly via Wi-Fi protocols or through a wired connection using Ethernet cables. Switches and routers within the LAN direct data to the correct devices, enabling fast and reliable data transmission. A diagram showing individual computers on the left side of the image, a cloud in the middle, and servers on the right. A line from the individual computers through the cloud shows the data flow. A shield is on the far right, with a box around the entire environment. Networks also need some level of privacy. A corporation, a school, or even a home needs a way to protect data, provide resources for specific people, and have a way to let some people in and keep others out. Imagine if your home didn't have a front door. Anyone could just walk into your house. Networks need similar gatekeeping, and LANs perform this work for you. When you set up a router for your home and use your Internet Service Provider, ISP, to connect to the Internet, you're setting up a LAN. When you enter a Wi-Fi password at a coffee shop, you're entering the shop's LAN. When inside, you can access special resources or access the wider world of the Internet. The Internet, billions of computers can find the ones they want to communicate with. The world from space. The Internet is a wide area network, WAN. As with PANs and LANs, a WAN refers to the distance the network can extend. WANs function similarly to LANs but cover a much wider geographic area. The Internet is a public WAN that covers the world, and now, even space. The Internet is considered an open WAN because devices don't need permission to access it. LANs, PANs, and WANs that require security credentials for access are considered closed networks. While closed WANs exist, they can get quite expensive because they require a secure way to transmit data between disparate and broad geographic areas. Building transmission lines that a single company will use, for example, is not always feasible. But what if a company wants to allow people from all over the world to access their network, and they need the security of a LAN but use the open WAN of the Internet to connect people to that LAN? The special technology required is called a virtual private network, VPN. Let's explore how VPN technology works. VPN and tunneling, how remote work gets done. A person using a tablet device that shows a VPN screen. Image source, photo by Dan Nelson, opens in a new tab, on Unsplash, opens in a new tab. Many people work remotely and need access to company files and directories. Many schools enable students to access the school's library and their course material from remote locations. Instead of requiring employees and students to download all the files and resources to their local computer, corporations and schools use a technology that enables people to access their private LAN remotely using the Internet. This saves companies and schools from installing private transmission cables across the world. A virtual private network, VPN, uses the infrastructure of the Internet to create a secure tunnel from one LAN to another LAN. Put another way, people use the open WAN of the Internet to connect two closed LANs. Think of each LAN as a person inside a room with a locked door. Between these locked rooms is a larger, open room, which represents the WAN or the Internet. Imagine a secure tunnel that goes from one locked room through the open room and ends at the other locked room. This tunnel is your VPN. To enter into each locked room from this tunnel, you need to use a specific passcode or digital key on the door. Now, if the two people in the locked rooms need to communicate with one another, they do so through a trusted messenger. This messenger takes a message from one person in a locked room, goes through the secure tunnel across the open room, and delivers the message to the person in the other locked room. Let's consider a scenario you might be familiar with, connecting a friend to your home Wi-Fi network. If a friend wants to connect to the Wi-Fi at your home, you would first give them the name of your Wi-Fi connection of the physical router inside your home. When your friend connects their device to the network, the system will ask them for a password, which you provide, allowing them to connect. Now, your friend is connected to your network through your router and can access everything available on your network. This includes seeing all connected devices, accessing files, and using the Internet. VPNs work in a similar way but with a clever twist. Instead of needing to be in the same physical location as the router, VPNs use the Internet to provide the connection. If you had a VPN set up for your home network, your friend would be able to connect to your network from anywhere else with an Internet connection. They would have access to all the resources on your network just as if they were inside your home, except they are accessing those resources from their location over the Internet. VPNs serve as a secure tunnel between remote devices and a private network. They allow users to access resources as if they were physically connected, enhancing both connectivity and security. You've just explored the three fundamental network types that enable connectivity. These network types are ways our devices communicate across different distances and environments. Whether it's a simple connection between a phone and smartwatch or a complex web that links global corporations, these networks connect us in the virtual world. Next, you'll examine the physical connections that enable these networks to function. Network cables. Fiber optic cables illuminated in a dark room. Network cables act as the roadways of a network, transmitting data across different distances and environments. From individual connections within a personal device to the vast web linking cities and continents, cables play a crucial role. Often, connectivity issues can arise from cable-related problems such as breaks, loose connections, or interference. A deep knowledge of different cable types allows IT support technicians to quickly identify and resolve these issues. IT support technicians might be involved in network cable maintenance tasks such as cable testing and termination. Termination means to attach a connector to the end of a cable to enable proper connection to a device or another cable. Additionally, IT support technicians might be responsible for splicing or joining two lengths of cable together to extend reach or repair a break. Let's explore three primary types of networking cables and how they are used. Coaxial, Ethernet, fiber optic. Coaxial cables. IT support technicians often find themselves interacting with coaxial cables in various contexts. Whether they are placing hardware for a new network, integrating with existing Ethernet configurations, or performing troubleshooting tasks, a deep understanding of coaxial cable properties is essential. When it comes to troubleshooting, technicians might need to measure signal strengths, identify points of interference, or ensure that connections are secure to maintain optimal network performance. Take a moment to review these illustrations of the cable to get familiar with its components. Notice from the previous illustrations that coaxial cables are engineered with multiple layers to achieve a specific set of characteristics. The core conductor, typically made of copper, serves as the primary channel for data and electrical signals. Surrounding this core is an insulating material that's designed to keep the signal intact. The next layer is a metallic shield, often made from a combination of aluminum and copper, which plays a vital role in reducing electromagnetic interference from external sources. The outer insulating layer provides physical protection to the inner components. Coaxial cables are typically terminated using an F-type connector. Use in networking. Coaxial cables are typically used in telephone, cable television, and internet services. For instance, they are used in older Ethernet configurations and can serve as an alternative when twisted pair or fiber optic solutions are not feasible. Their shielding capabilities make them an excellent choice for environments that require additional protection against interference, such as industrial settings or healthcare facilities. Select each tab to learn more about the pros and cons of using coaxial cables in networking. Pros. Durability. Coaxial cables are known for their robust construction, making them resistant to physical damage and environmental factors such as temperature changes. Interference shielding. The unique layering technique offers excellent shielding against both electromagnetic and radio frequency interference. Distance capability. These cables can transmit data effectively over longer distances compared to some other types, without the need for frequent signal boosters or repeaters. Cons. Flexibility. Because of their thickness and layering, coaxial cables are less flexible and might require more complex installation processes. Cost. The additional shielding and durable construction come with a higher price tag for both the cables themselves and the connectors. Limited bandwidth. While suitable for many applications, the bandwidth limitations become evident when compared to more modern solutions such as fiber optic cables. Ethernet cables. IT support technicians play a role in the implementation and maintenance of Ethernet-based networks. This includes selecting the appropriate type of cable and the correct category. They are also the frontline troubleshooters when connectivity issues arise, identifying whether problems stem from the cables themselves, the network configuration, or external interference. Ethernet cables are mostly used for LANs. Take a moment to review these illustrations of the cable to get familiar with its components. Ethernet cables are constructed with multiple pairs of color-coded insulated copper wires. These pairs are twisted together to minimize electromagnetic interference and then enclosed in an insulating jacket. This is why they are commonly referred to as twisted pair cables. They are typically terminated with an RJ45 connector. The two main categories of twisted pair cables used in Ethernet networks are the unshielded twisted pair, UTP, cable in which pairs of wires are wrapped in an outer jacket. Shielded twisted pair, STP, cable in which each pair of wires is wrapped in foil shielding and then wrapped in an outer jacket. Ethernet cables are available in different categories. Select each card to learn more about the different categories of Ethernet cables. Cat5. Typically manufactured as UTP and used for home internet connectivity, small office/home office networks, and older LANs with speeds up to 100 Mbps. Cat5e. An enhanced version of Cat5, these are usually manufactured as UTP. They are used for LANs, including small and medium-sized business networks, and are also a popular choice for home networks with higher bandwidth needs, such as HD video streaming and online gaming. They support speeds up to 1 Gbps and offer better performance than Cat5 cables. Cat6. These cables can be manufactured as either UTP or STP. They are generally used in LANs that require higher data rates and lower levels of interference than Cat5 or Cat5e cables. This includes medium to large office environments, some data centers, and for use in professional audio and video setups. They are designed for high data rates of up to 10 Gbps but are limited to shorter distances than Cat5e cables. Cat7. These cables are always manufactured as STP. They are designed for the highest performance, and they support speeds up to 100 Gbps over short distances. They are used in most data centers, and large enterprise office networks. Use in networking. Ethernet cables are the backbone of most local area networks, LANs. They connect various network devices such as computers, switches, and routers, facilitating data transmission across the network. Depending on the environment and the specific networking requirements, IT support technicians might choose from the different categories of Ethernet cables for optimal performance. Select each tab to learn more about the pros and cons of using Ethernet cables in networking. Pros. Affordability, especially for UTP cables, the cost is relatively low, making them a frequent choice for many networking projects. Flexibility, these cables are easy to bend and install, making them suitable for a variety of setups. Versatility, with various categories available, Ethernet cables can be selected to match the specific needs for speed and bandwidth. Cons. Interference, particularly for UTP cables, susceptibility to external interference can be an issue if the cables are not adequately isolated or if they are running parallel to electrical lines. Distance limitations, signal quality can deteriorate over longer distances without the use of signal boosters or repeaters. Bandwidth, while they are catching up, Ethernet cables still generally offer lower data rates compared to fiber optic cables. Fiber optic cables. For IT support technicians, working with fiber optic cables is often specialized work. They might be responsible for troubleshooting any connectivity issues, which can include tasks ranging from signal quality checks to potentially intricate repairs. So, an understanding of fiber optic characteristics and the tools required for testing and repair is useful. Take a moment to review these illustrations of the cable to get familiar with its components. Fiber optic cables are fundamentally different from copper-based cables such as coaxial and Ethernet cables. Instead of using electrical signals, they use light to transmit data. The core of these cables consists of strands of glass or plastic fibers. These are surrounded by a layer called the cladding, which reflects the light back into the core, allowing data to travel great distances with minimal loss. Finally, a protective outer jacket encases these internal components. They are commonly terminated with straight tip connectors and lucent connectors. The two main categories of fiber optic cables include the following. Single mode is designed to transmit a single ray of light. A single ray of light is also known as a mode. Single mode is best suited for long-distance data transmission with high bandwidth. Multi-mode is designed to allow multiple rays of light to travel through the core simultaneously. It is more appropriate for shorter distances and is commonly used within buildings or campuses. Use in networking. Fiber optic cables are widely used in high-speed, high-bandwidth applications. They are commonly found in internet backbones, data centers, and increasingly in more localized settings like campus networks. With the capability to transmit data over long distances without signal degradation, they're ideal for connecting geographically dispersed networks. Fiber optic cables are useful in ones because of their remarkable speed and capacity over long distances. Select each tab to learn more about the pros and cons of using fiber optic cables in networking. Pros. High data rates. Fiber optic cables offer extremely high data rates, often measured in gigabytes per second, Gbps, or even terabytes per second, Tbps, making them ideal for data-intensive applications. Long-distance transmission. These cables can transmit data over great distances with minimal signal loss, reducing the need for signal boosters and repeaters. Immunity to interference. Fiber optic cables are immune to electromagnetic interference, making them ideal for environments with high levels of such interference. Cons. Cost. High-quality fiber optic cables, along with their specialized connectors and installation, can be expensive. Fragility. The glass or plastic fibers within the cable are delicate and can be damaged if bent beyond their specified bend radius. Skill requirement. Installation and maintenance require specialized skills and equipment, making it less straightforward than installing copper-based cables. There is another type of cable crucial to networking that IT support technicians rarely engage with directly, called submarine communication cables. Submarine communications cables. While detailed knowledge of submarine communications cables is not typically a requirement for IT support technicians, having a basic understanding can be beneficial. Submarine communications cables serve as the backbone for global internet, voice, and data communication, connecting continents and enabling international networking. Disruptions in these can have downstream effects on enterprise or local networks that technicians may be responsible for. Knowing about the larger infrastructure can help provide a broader context when troubleshooting network issues that involve internet connectivity, especially for businesses that rely on international data transmission. Take a moment to review this illustration of the cable to get familiar with its components. Submarine communications cables are complex cables that often combine both fiber optic and copper elements. The fiber optic strands facilitate high-speed data transmission, while copper elements are typically used for power delivery to amplifiers or repeaters along the cable's length. Network cables work together. Sending a document from your computer to cloud storage is a common yet intricate process involving various types of cables and network equipment. Here's how sending a document works within LANs and WANs. Local area networks, LANs. Computer to router/switch, Ethernet. Your document starts on the LAN. On a LAN, when you send a document from a computer, it first travels through a Cat5e or Cat6 cable to the router or switch. These Ethernet cables provide the necessary bandwidth and reduce interference, ensuring a smooth transition. Router to wireless access point, Ethernet. The data then moves to a WAP also using Cat5e or Cat6 cables. These cables are cost-effective and commonly used to connect different equipment within LANs. Through repeaters and bridges, coaxial. If the LAN is extensive, the LAN might use repeaters and coaxial cables to connect them. Bridges within a LAN might also use these cables to efficiently link different network segments. Router to WAN, fiber optic. Next, the document moves to the WAN or Internet to complete its journey to cloud storage. When the document begins traveling outside the local network to cloud storage, fiber optic cables come into play, transmitting the data over long distances at incredible speeds. WAN to cloud storage, fiber optic/copper. The data's journey to cloud storage might involve several routers, switches, and network interface cards, NICs, interconnected by a combination of fiber optic and copper cables. Cables are the backbone of networking. They transmit data across different distances, acting as the roadways of the network. Commonly used cables like coaxial, Ethernet, and fiber optic each have specific roles and applications. As you just explored, the process of sending a document from a computer to cloud storage requires each of these cables to work together within LANs and WANs to ensure smooth and efficient data flow. Activity: differentiate between types of network cables. Employability skills. Attention to detail. You've learned a lot about network cables. IT support technicians use them to connect different types of network devices, in different types of networks. In this activity, you'll choose the appropriate type of cable based on a scenario that includes networking needs. Summary and looking ahead. In this lesson, you've learned about the essential components of networking, including the various types of hardware, such as routers, switches, and WAPs. You also explored 3 network types: PANs, LANs, and WANs. And you discovered how coaxial, Ethernet, fiber optic, and submarine communication cables enable smooth data flow over networks. This knowledge sets the foundation for the next lesson, in which you will learn the process to properly place network hardware. This is an essential skill for IT support technicians and anyone looking to work with or maintain network systems. About this lesson: place and upgrade network hardware. Suppose you are asked to upgrade a small company network. Where would you begin? What would you need to know? What process would you follow? In this lesson, you'll learn how to place network hardware and walk through the steps an IT support technician takes. You'll also learn the steps to place network cables and connectors. Then, you'll learn about when to upgrade a network and the steps to follow when it's time to upgrade a network. Network assembly and physical installation. Each component in a network architecture enables certain functionality or solves a specific problem. Network architecture refers to the design and structure of a network, including the physical and logical layout and the set of rules that determine how the network's components interact. The term reflects the importance of constructing the network structure so each piece of hardware can do what it was designed to do and enhance the overall performance of the network. a man working with network cables at a network control panel. When determining the proper placement of networking components, it's important to consider the role each component plays within the entire network architecture. Positioning the components properly ensures that data travels seamlessly, swiftly, and securely across the network. The careful orchestration of these components is akin to conducting a symphony. Each network component plays a vital role in creating harmonious communication within and between networks. Placing network hardware. The right hardware in the right place creates a robust and reliable network system, whether it's routers connecting distant networks or switches ensuring smooth traffic within a single network. In large organizations, a network engineer designs, implements, and manages the assembly of a network with support from a technician. But, in certain organizations, IT support technicians can be responsible for placing network hardware to create a robust and reliable network system. Let's learn about each step in the process of placing network hardware. Placing the routers and switches. An IT support technician works alongside a network engineer in placing routers and switches. They will assist in assessing the network's requirements, including size and layout. They provide physical assistance in locating and positioning these essential network components and play a role in optimizing their placement. This includes understanding the overall network plan, ensuring proper alignment, and managing physical constraints to guarantee optimal performance and security. Assess the network requirements. The network engineer, with support from the technician, determines the size and layout of the network by identifying the number of users, devices, and the types of data that the network will primarily be transmitting. Place the routers. The technician locates routers at the junctions where different networks meet and ensures proper security measures. Routers act as gateways between networks. Position the switches. The technician places switches within individual network segments, ensuring that the switches are located near the devices they serve for optimal performance. Placing client-facing network hardware. The network engineer architects the network solution to define the requirements and determine how much equipment the network will need to meet technical requirements. The IT support technician's responsibilities when placing client-facing network hardware include physical installation, testing coverage, aligning with compatibility requirements, and assisting with the strategic positioning of the components. The technician's role is instrumental in ensuring that client devices can seamlessly connect to the network and that the network's range is extended as needed. Install WAPs. The technician strategically places WAPs according to the network engineer's architecture to provide maximum wireless coverage, considering physical barriers like walls that might affect signal strength. Configure NICs. The technician installs NICs in devices that need to connect to the network, being mindful of compatibility with the network's protocols. Set up repeaters. The technician determines areas where the network signal weakens. They place repeaters in these locations to extend the network's range. Implement bridges. The technician identifies segments within the network that need interconnection and places bridges to filter and control traffic between these segments. Testing, documenting, and maintaining network hardware installations. During the testing, documenting, and maintaining phase, the IT support technician collaborates with the network engineer to ensure that all network components are working cohesively. They assist in running tests, monitoring tools, and maintaining detailed records of the installation, including hardware placements and configurations. Test and monitor. The technician tests the network to ensure that all components are working together efficiently, monitors the network regularly for performance, and adjusts as needed. Document the setup. The technician keeps a detailed record of the hardware placements, configurations, and network topology. This information will assist them in troubleshooting and future network expansions. Provide ongoing maintenance. The technician regularly reviews the network's performance, makes necessary adjustments, and considers potentially scaling the network to allow for future growth or changes. IT support technicians also support ongoing maintenance by participating in routine inspections, making necessary adjustments, and helping in scaling or modifying the network to keep it running efficiently. Their continued support contributes to the long-term success and adaptability of the network. Placing network cables and connectors. A server rack showing a network meter with a cable in the meter and a cable in the rack. Even though much of the data transmitted in modern networks is transmitted to devices wirelessly, cables and connectors are still the fastest and most reliable way to get data from one place to another. The selection, installation, and termination of network cables and connectors is an essential aspect of building a fast, resilient network that users can rely on. IT support technicians might never have to install network cables, but they often have to troubleshoot network connections. Much like understanding the types of network cables can help diagnose and resolve network troubleshooting issues, understanding the process network engineers follow to connect network devices using cables and connectors can also help technicians troubleshoot issues. In some roles, the IT support technician plays a supportive role during the network installation process. Let's learn about each step of the process of choosing and placing network cables and connectors. Planning and gathering requirements. An IT support technician collaborates closely with network engineers to get a full understanding of the network's needs, the types of cables and connectors chosen, and the planned route for those cables. While the network engineer takes the lead in identifying what the network requires, choosing the right cables, and laying out the cable path, the technician's role is to be well informed about these decisions. This knowledge prepares the technician for future support and troubleshooting. Select each tab to learn more about planning and gathering requirements. Identify. Identify the network's requirements. Determine the network requirements, including type of network, network size, bandwidth requirements, distance between devices. Consider environmental factors such as electromagnetic interference that might affect certain cable types. Select. Select the appropriate cables and connectors. Choose Ethernet cables for general purposes, considering the specific category needed, such as Cat5e or Cat6. Select fiber optic cables for longer distances or higher bandwidth needs. Ensure that the connectors are compatible with the chosen cables. Plan. Plan the cable path. Map out the route the cables will take, avoiding areas with high electrical interference. Consider using conduits or cable trays to protect and organize the cables. Installing the cables. The technician provides support to the network engineer in measuring, cutting, installing, and terminating the cables. This support might include handling tools, helping with measurements, or physically assisting in the laying and organization of cables. Select each tab to learn more about installing cables. Measure and cut the cables. Measure the lengths required, adding extra cable for slack and future adjustments. Cut the cables carefully by using appropriate tools, such as cable-specific cable cutters and strippers. Install the cables. Run the cables along the planned path, avoiding sharp bends and twists. Use cable management techniques to keep cables organized and protected. Terminate the cables. Strip the insulation from the ends of the cables using cable strippers. Attach the appropriate connectors using the correct tools. A crimping tool for coaxial cables and F-type connectors. A crimping tool for Ethernet and RJ45 connectors. A fusion splicer for fiber optic and standard connectors, SC, straight tip connectors, ST, or lucent connectors, LC. Follow the specific wiring standards. Coaxial cables often use the RG6 or RG59 standard. Ethernet cables use T568A or T568B standards. Testing, documenting, and maintaining network cable installations. The technician works together with the network engineer to perform tests on connections and to ensure that all documentation is accurate and complete. Test the connections. Check that the cables and connectors are functioning properly by using a cable tester to check for continuity. Ensure that data can travel end-to-end through the cable. Proper pin configuration. Match the network standard you are using. Cable integrity. Check for the absence of shorts or crossovers. Document the installation. Keep detailed records of the cable types, paths, and termination points. Detailed records are vital for maintenance, troubleshooting, and future upgrades. Monitor and maintain cables. Regularly inspect cables and connectors for wear or damage. Make necessary repairs or replacements promptly to prevent network issues. The technician provides continuous monitoring and maintenance of the cables and connectors, such as regular inspection for wear or damage. The technician is responsible for carrying out repairs or installing replacements to prevent or address network issues. Having intimate knowledge of the cable paths and termination points as documented is critical for these tasks. Additional network support tasks. In addition to assembling and installing networks, IT support technicians are responsible for other tasks, such as the following: user support and training. IT support technicians provide assistance and training to users on how to use the network properly. They will also troubleshoot minor connectivity problems that users might face. Compliance with standards and guidelines. IT support technicians ensure that all support and maintenance activities follow industry standards and organizational guidelines that are referenced in the installation process. Ensuring compliance helps maintain the integrity and efficiency of the network. The IT support technician plays a supportive role during the network installation process and a primary role in the ongoing care and maintenance of network cabling. The technician's responsibilities include the following: understanding the network design, assisting in installation, performing quality checks, providing continuing support and maintenance. By aligning their work with the detailed process carried out by the network engineer, IT support technicians ensure that the network functions effectively and remains robust over time. Network upgrades. When to upgrade. 2 technicians working in a server room. Over time, network hardware might become obsolete or unable to support the growing demands of the organization. This is the point where upgrading becomes essential. Upgrading network hardware can lead to improved performance, enhanced security, and the ability to integrate new technologies that align with business goals. In an organization, the responsibility for determining when a network upgrade is necessary often falls under the domain of IT management, including IT directors and network administrators. They collaborate to make informed decisions about when and how to upgrade the network. And IT support technicians can also play a role in helping network administrators and IT management determine whether an upgrade is necessary. Their hands-on experience in dealing with day-to-day network issues and user interactions provides them with practical insights that can contribute to the decision-making process. The decision to upgrade individual network hardware components isn't always straightforward. Explore the following guidelines to help determine how and when an upgrade might be necessary. 1. Performance evaluation. IT support technicians are often the first point of contact for users experiencing network-related problems. They can report recurring problems or common network complaints. They might also monitor the network's responsiveness and efficiency to identify any signs of slowdown or inefficiency. 2. Compatibility issues. Technicians might closely monitor for any abnormal behavior or errors that occur following the implementation of new software. When new software or applications are introduced, the existing networking hardware might be incompatible. If the new software requires greater processing power, bandwidth, or specific capabilities beyond what the current hardware can offer, they might identify the need for a network upgrade and recommend considering a network upgrade to maintain seamless operation and achieve optimal performance. 3. Security concerns. Older hardware might not support the latest security protocols. When IT support technicians notice that existing systems begin to show vulnerabilities, such as failing to meet compliance standards or struggling to fend off malware and other cyber threats, they might identify it's time to upgrade. Upgrading to newer hardware enhances the network's defense against potential threats. 4. Vendor support. Sometimes, manufacturers discontinue support for older models. If IT support technicians encounter error messages due to failed updates, it can signal discontinued support for that specific model. They might recommend an upgrade to a supported model to ensure that the component will continue to receive critical updates and technical assistance. 5. Strategic alignment, ensuring that the hardware aligns with the organization's strategic goals and future growth plans is vital. An upgrade might be in line if the current system doesn't support new business initiatives or expansion. For example, if an online retailer's current network struggles to handle increased online orders and customer data, it's a clear indication that an upgrade is necessary. While IT management is responsible for determining if hardware is in alignment, they might request data and user feedback from IT support technicians. 6. Technology trends. Staying up to date on the latest technology trends and industry standards can also guide the decision to upgrade. Implementing new technologies, such as artificial intelligence, might require hardware that can support them. It is essential for all IT roles in an organization, including network administrators and IT support technicians, to keep current on new technologies and what networking hardware they might require. Now that you've explored the role an IT support technician plays in determining when to upgrade a network, let's review the process for upgrading a network. Upgrading a network. Female technician checking network servers using a tablet. Upgrading network hardware is a deliberate and essential process that ensures the enterprise network continues to function efficiently and securely. In an organization, network administrators and IT management collaborate to assess the network's needs, plan the upgrade strategy, acquire necessary hardware and software, coordinate implementation, and ensure a seamless transition. IT support technicians are often involved in supporting network administrators in the network upgrade process. Introduction. Review the following process for a step-by-step guide so you understand what's involved in upgrading networking hardware from an IT support technician's perspective. Step 1. Assessing the current network. The IT management team and network administrators assess the current network by evaluating existing hardware to understand their capabilities and limitations. Determining if existing hardware is compatible with new software or technology. Matching hardware to organizational needs such as growth plans and intended functionality. In this step, an IT support technician might support the IT management team by providing information about existing hardware and its capabilities. Step 2. Planning and preparing for the upgrade. The IT management team and network administrators plan and prepare for the upgrade by selecting appropriate hardware that best suits the network's requirements and anticipated growth. Scheduling downtime to minimize disruptions and inconvenience to users. Communicating with stakeholders and informing them about the upgrade plans, potential downtime, and expected benefits. In this step, an IT support technician might work with management to help determine the appropriate hardware to meet the organization's requirements. Step 3. Implementing the upgrade. IT support technicians collaborate closely with network administrators to implement the network upgrade. The tasks to implement the upgrade include replacing or upgrading hardware such as routers and switches. Following safety protocols to maintain a secure work environment. Coordinating with other teams, such as security, operations, and support, to ensure a synchronized approach to the upgrade process. In this step, the IT support technician is responsible for physically installing the new hardware while following all safety protocols to maintain a secure work environment. For example, they might replace an old router with a new one, ensuring all cables are correctly connected and safety protocols have been followed. Step 4. Testing and verifying the upgrade. IT support technicians and network administrators both test and verify the upgrade by conducting tests, including performance testing, load testing, and compatibility testing. Verifying correct installation, checking cable placement, and ensuring they function as intended within the network environment. Documenting the upgrade process. In this step, an IT support technician assists the network administrator in conducting performance and load testing. They might also check cable placement and be responsible for documenting the upgrade process. Step 5. Performing maintenance and support. IT support technicians and network administrators are both responsible for performing maintenance and support, including implementing regular maintenance schedules, providing ongoing support, troubleshooting issues as they occur. Ongoing care ensures that the network continues to perform optimally. An IT support technician implements regular checks and maintenance, such as monitoring the network for potential failures or areas for further optimization. They also provide ongoing support for the network and troubleshoot any issues as they occur. Next, you will complete an activity based on what you've learned about upgrading a network and placing network hardware. Activity: placing network hardware for an upgrade. Employability skills. Analytical thinking. In this activity, you're an IT support technician who has been assigned the task of supporting Fatima, a network engineer, during the upgrade of a small company's network. Together, you will be choosing and placing network hardware. You and Fatima must follow these requirements. Connect two physically separate offices securely. Provide wireless access. Handle high data volumes. Minimize cost and complexity. Follow along with Fatima to assist her by using your knowledge of planning network hardware, cables, and connectors. You'll answer questions as you perform the steps to place network hardware to upgrade the network. Assessing the network. Fatima knows that understanding the previous setup and existing hardware is vital. By surveying the layout, devices, and data types, she can identify what the two of you can reuse and what needs to be replaced. To complete this step, Fatima does the following. Surveys the existing layout of the network, including the current organization of components and connections. Examines the devices that are part of the network, looking at their condition, functionality, and their integrations. Identifies the types of data that the network is primarily transmitting. This identification helps Fatima understand what kinds of communication or information the network is processing. Determines what parts of the existing setup can be reused or need to be replaced. This conclusion helps save costs and ensure compatibility within the network. Illustration of two people assessing a network installation. Planning and preparing for an upgrade. Before you and Fatima can place the upgraded network hardware, Fatima must finalize the plan and prepare for the implementation. To complete this step, Fatima does the following. Evaluates hardware options that align with the network's requirements and anticipated growth, ensuring optimal performance and scalability. Strategically schedules downtime to minimize disruptions and inconvenience to users, enabling a smooth transition during the upgrade process. Recognizes the importance of clear communication and keeps stakeholders informed about the upgrade plans, potential downtime, and expected benefits. This transparent approach fosters understanding and collaboration throughout the process. Illustration of two people with a network installation plan. Placing routers. Fatima makes the decision to use two routers to create a secure VPN tunnel between offices. This step is critical for safeguarding data. The routers act as gateways between networks, and proper security measures are essential to protect information. Fatima considers a few factors before placing the routers, including the following. The network's overall structure. The network's security needs. How the new routers will integrate with the existing network and other hardware. How the new routers will function to meet the network's specific requirements. Illustration of a few routers in an office space. Positioning the switches. After the routers are in place, Fatima places a central switch in each office to connect all devices within their local networks. She chooses gigabit Ethernet switches because of the need for high-speed data transfer to reduce network congestion, a common bottleneck in busy networks. To place switches in the right positions, Fatima takes the following into account. The layout of each office and the optimal central location for the switches that will allow them to connect all devices within their local networks effectively. The current and anticipated volume of data transfer within the network affects the decision to use Gigabit Ethernet. Scalability of the new network. Fatima wants to ensure that the network can adapt to future growth or changes in technology. Placing wireless access points, WAPs. Fatima understands the need for mobility and guest access. By strategically placing WAPs, she can ensure that no barriers, such as walls, impede signal strength, creating an environment where connectivity is always at hand. Illustration of wireless access points in an office space. Implementing bridges. This complex network step encompasses connecting segments with different architectures. Fatima decides to use bridges to ensure that all parts of the network can communicate efficiently. She must review the different architectures within the network segments to determine what specific types of bridges the network needs. She must review the need for bridges to decide between the following. Wired and wireless networks. Bridging might be necessary to facilitate communication between wired and wireless segments within the network. Different speeds or bandwidths. In cases where segments operate at different speeds or have different bandwidth capacities, a bridge can help balance and regulate network traffic, preventing bottlenecks. Testing and monitoring. You thoroughly test the new network as a step to catch potential issues early. Using specialized tools, you ensure that all components are working together efficiently. You use the following tools in testing and monitoring. Network analyzers. These tools analyze the overall performance and health of the network. They can detect abnormalities or issues in data transmission, allowing for early intervention and resolution. Protocol analyzers or packet sniffers. Protocol analyzers capture and analyze data packets as they travel through the network. They test network behavior and are often used for troubleshooting specific issues, such as identifying misconfigured network devices causing communication errors. Ping and trace route tools. Ping and trace route are basic utilities that test the reachability of hosts on the network and the paths that packets take. They are commonly used to diagnose connectivity problems and to map network topology. Bandwidth monitoring tools. These tools monitor the flow of data and the utilization of the network's bandwidth. By tracking bandwidth usage, they help to identify and prevent potential congestion or bottlenecks within the network. Illustration of a man and a woman monitoring a network installation. Documenting and supporting maintenance. Fatima knows that proper documentation is an investment in the network's future, allowing for smooth troubleshooting that might be required at a later time. She documents the network hardware that was installed, issues that were encountered during installation, and plans to resolve any issues that were identified during testing. In the end, the careful planning, understanding of complex needs, and ability to think strategically culminated in a robust network that met the requirements of the business. Your success was not just in the technical skills but also in your ability to apply those skills thoughtfully, turning a set of complex tasks into a finely tuned system. What do you think? Critical thinking. Considering the goal and requirements of this network upgrade project, can you identify an alternative solution or additional considerations that Fatima could have made? Evaluate your thinking. Does your answer account for the following? Energy efficiency considerations. Fatima could have considered the energy efficiency of the devices and layout. Using energy-efficient hardware and designing the network to minimize energy consumption might have had long-term cost-saving implications and aligned with environmental sustainability goals. User training and support. Fatima could have considered developing user guides or conducting training sessions to ensure that employees knew how to use the network effectively and safely. Disaster recovery planning. Fatima could have considered making a disaster recovery plan. Adding redundancy and a recovery strategy might have increased the resilience of the network, ensuring business continuity in case of hardware failure or other unforeseen events. Upgrading network hardware is a necessary process that ensures the network continues to function efficiently and securely. Regular assessments and alignment with organizational goals are key factors in determining when individual network hardware components should be upgraded. Proper planning, careful implementation, and testing are key to successfully upgrading a network. Summary and looking ahead. In this lesson, you followed the process to place network hardware. You learned about assessing the network requirements, placing routers and switches, installing WAPs, configuring NICs, setting up repeaters and bridges, testing, documentation, and providing maintenance. You also learned about placing network cables and connectors. Finally, you explored how to determine when network components need to be upgraded and the steps to upgrade a network. In the next lesson, you will learn about common network hardware issues and techniques to troubleshoot them. About this lesson, troubleshooting networks. We've all ridden on highways. But what would it be like to ride on a computer network? We jump on a lightning speed connection surrounded by data, images, and videos of every kind. Network devices such as routers and switches would whisk us through traffic. We would hum along, switching among multiple lanes as every piece of hardware making up the highway keeps us headed smoothly to our destination. But wait, it's all slowing down, and we see damaged connectors, and it feels like we're heating up. We're suddenly squeezing through a small tunnel, and a sign ahead flashes inadequate bandwidth. What happened to our ride? In this lesson, you will learn about network hardware issues and their symptoms. You will learn techniques to troubleshoot these issues and preventative maintenance best practices to keep a network at optimal performance. Importance of identifying issues early. In today's interconnected world, networks act as highways for information, allowing users to access, share, and store data. Whether it's a multinational corporation managing vast amounts of data or a small family streaming their favorite shows, network hardware enables these activities to occur seamlessly. Just as a well-maintained road allows for smooth driving, network hardware must be kept in optimal condition to ensure robust and reliable connections. Similar to how roads can experience wear, network hardware can deteriorate, which disrupts these smooth connections. IT support technicians help keep these connections running smoothly. They must identify common network hardware problems and their symptoms so that networks stay efficient and secure. It's also important for the longevity of the hardware and user satisfaction. Select each tab to learn more about why it is important to identify common network hardware problems. Efficiency. Recognizing symptoms early can lead to quicker resolutions, minimizing downtime, and keeping the flow of information uninterrupted. Imagine an employee notices that the company's internet is increasingly slow during peak hours. By identifying the symptom early, the IT support technician can locate and replace a failing switch before it causes a network outage. Security. Some issues might expose the network to security risks. For example, outdated firmware often lacks the latest security patches, making the device more susceptible to unauthorized access or attacks. Understanding these problems helps fortify the network against potential threats, such as hackers gaining access to sensitive data. Longevity. Regular monitoring and maintenance can prevent minor problems from becoming major failures, thus prolonging the life of the hardware and saving resources. For example, an overheating router can lead to hardware failure if not addressed promptly. Regular monitoring might detect the temperature increase, allowing time for corrective action, such as improving ventilation. This preventive measure can extend the life of the router. User satisfaction. A well-maintained network provides a better user experience, whether it's faster internet speed or more reliable connections. Now that you know why it is important to identify common issues early, let's explore how to identify common issues. Common network hardware issues and their symptoms. There are many common network hardware issues, ranging from outdated firmware to faulty connections. By being aware of these issues and their symptoms, IT support technicians can proactively diagnose and address problems. This minimizes downtime and potential disruptions to the organization. Whether it's a failure in a router, a slowdown in connection speed, or compatibility issues with new software, technicians can tackle these challenges effectively with timely intervention. Select each section to learn more about common network hardware issues and their symptoms. Faulty cables and connectors. Cables and connectors that are damaged or improperly connected can cause significant delays in data transmission. They lead to slow data traffic and bottlenecks, making data transmission difficult and sluggish. Symptoms to observe: slow internet speed, intermittent connection. Overheated devices. Network devices, such as routers and switches, can overheat because of poor ventilation or heavy usage, which can lead to decreased performance or even failure. Devices can also overheat due to cause being placed in an area with poor airflow or because they have accumulated dust. Overheated routers and switches slow down the flow of traffic and can lead to network failures. Symptoms to observe: unexpected shutdowns, sluggish performance. Outdated firmware. Without regular updates, network hardware might become susceptible to security risks or might not work well with newer technologies. Using outdated firmware can result in the data going to the wrong place and security vulnerabilities. Symptoms to observe: unauthorized access, multiple failed login attempts, incompatibility with newer devices. Router and switch failures. Routers and switches are essential devices that manage data traffic. Failures here can lead to network congestion or complete loss of connectivity. Failures with this equipment can cause network congestion, data loss, and sometimes data stops flowing completely. Symptoms to observe: network slowdown, inability to connect to the internet. Inadequate bandwidth. Insufficient bandwidth refers to the lack of adequate data transfer capacity in a network to handle the volume of data being sent and received, leading to slow data transmission rates and potential network congestion. Symptoms to observe: slow internet speed, especially during peak usage times. Signal interference. Other electronic devices or physical obstructions can interfere with Wi-Fi signals, leading to poor connectivity. Signal interference in a network can result in weak connections and frequent drops. Symptoms to observe: weak Wi-Fi signals, connection drops. Hardware configuration errors. Incorrectly configured hardware can lead to an unstable network and potential security risks such as interception. Symptoms to observe: inconsistent network performance, security issues. Wear and tear. Like all physical equipment, network hardware can deteriorate over time, leading to a decline in performance or sudden malfunctions. Deterioration leads to a gradual decline in performance, unexpected failures, and the need for repairs or replacements. Symptoms to observe: gradual decline in performance, unexpected hardware failure. Malfunctioning network interface cards, NICs. NICs connect computers to networks. A malfunctioning NIC can create connectivity problems for individual computers. If NICs don't function properly, data can't enter or exit the device smoothly, leading to unstable or non-existent connections. Symptoms to observe: inability to connect to the network, sporadic connectivity. Understanding common network hardware problems and their symptoms is a key aspect of maintaining a robust and efficient network. But recognizing a problem is only part of the solution. The next phase is applying the right techniques to diagnose these issues. In the following section, you'll examine techniques for troubleshooting network hardware to keep networks running smoothly and securely. Techniques for troubleshooting network hardware issues. Network reliability is crucial for businesses to deliver seamless services. IT support technicians often face complex challenges when maintaining network hardware. From slow internet speeds to potential security vulnerabilities, effective troubleshooting techniques are important to resolve network issues. Explore the challenges and steps an IT support technician takes to troubleshoot network hardware issues. The assignment: a network in trouble. Katrina is in her first week at Athene Video, a prominent video streaming service. As the newest IT support technician on the team, she is assigned to investigate a series of perplexing network issues that are surfacing. Employees are complaining of slow internet speeds and connection drops. The IT support team is inundated with tickets about weak Wi-Fi signals, and the security team is raising concerns about potential vulnerabilities. Female technician working with documents in front of a computer in a server room. The investigation. Katrina starts her investigation by thoroughly examining the symptoms. She observes the slow internet speed firsthand. She experiences intermittent connections while testing various devices. She closely examines the NICs, which reveal sporadic connectivity. The NIC devices themselves are showing signs of overheating, leading to sluggish performance. One thing is becoming clear to Katrina: these symptoms are not isolated incidents, but rather indicators of underlying problems within the network hardware. She is observing inadequate bandwidth, hardware configuration errors, and some simple wear and tear on hardware. Each of these symptoms points to a specific issue that needs attention. The problems. As the week progresses, Katrina meticulously documents her findings, aligning the symptoms with possible explanations. The problems include faulty cables and connectors, outdated firmware, and router and switch failures. By the end of the week, she completes a comprehensive report of the network's condition. It is time to move from diagnosis to action. The path forward. With a clear understanding of the problems, Katrina organizes her tools and prepares her troubleshooting plan. She knows that the next phase will be challenging, but she is ready to troubleshoot. Next, you'll learn troubleshooting techniques that IT support technicians like Katrina use to troubleshoot network hardware issues. Network troubleshooting techniques. A male technician inspecting networking hardware in a server room with his laptop and mobile device. Network hardware issues can disrupt the smooth functioning of an organization's daily operations. IT support technicians must identify the right techniques for troubleshooting to quickly diagnose problems. Let's learn about common troubleshooting techniques they use for network hardware. Analyze symptoms. Start by analyzing the reported symptoms, such as slow internet speed or intermittent connection, to understand the nature of the problem. Use diagnostic tools. Use network diagnostic tools to gather information about the state of the network. For example, technicians use the ping command to check if a host is reachable. The trace route command to show the path that packets take to reach a destination. Network analyzers, such as Wireshark, that can capture and display detailed network traffic data for deeper analysis. Inspect physical components. Inspect cables, connectors, and devices for visible damage or improper connections. Look for frayed cables, loose connections, or signs of wear that can affect performance. Inspect software. Check for outdated firmware, incorrect configurations, and compatibility issues with newer technologies. Review settings and consult vendor documentation for guidelines on proper configuration. Isolate hardware components. If a problem is difficult to identify, isolating individual components can help pinpoint the faulty hardware. For example, disconnecting one device at a time and observing network behavior can help isolate a malfunctioning device. Monitor network performance. Continuous monitoring of network performance and hardware health can reveal underlying issues before they become critical problems. Tools such as SolarWinds or Nagios can provide real-time insights. Consult documentation. Manuals and technical documentation provide insights into specific hardware functions, error messages, and troubleshooting steps. Documentation might also provide acceptable ranges and limits for issues such as high memory usage and packet loss. Always refer to the manufacturer's guidelines for specific procedures. Troubleshooting network hardware issues can be a complex task that often involves many variables, challenges, and ambiguities. In some situations, a technician might need to apply more than one troubleshooting technique to find the issue. Factors that can impact network troubleshooting. As with many troubleshooting tasks, applying proven techniques isn't always a straightforward exercise. Many times, you might have to apply a certain technique multiple times after you've gathered new information or ruled out a potential problem. For network hardware, you should consider several factors when attempting to troubleshoot a problem. Study the following list to become aware of these factors and how they can help inform your troubleshooting process. 1. Symptom overlap. Many network hardware problems exhibit similar symptoms. For example, slow internet speed can be caused by outdated firmware, inadequate bandwidth, or even faulty cables. Distinguishing between these causes requires careful analysis and might involve trial and error. 2. Lack of clear documentation. Not all hardware comes with comprehensive documentation, and what's available might not cover every potential issue. This lack of clear guidance can make it difficult to determine the best approach to troubleshooting a particular problem. 3. Interconnected systems. Network hardware often operates within a complex ecosystem where devices are interconnected. An issue in one part of the system can have cascading effects, making it challenging to isolate the root cause. 4. Incompatibility issues. With constant technological advancements, compatibility can become a hindrance. A piece of hardware that functions well with one device might conflict with another, and identifying these incompatibilities requires a deep understanding of the systems involved. 5. Environmental factors. Sometimes, the problems aren't in the hardware itself but in the surrounding environment. Issues such as overheating might not be caused by devices malfunction but by inadequate ventilation in the room. Recognizing these external factors requires a holistic view. 6. Dynamic network conditions. Network conditions change frequently, with variations in traffic, user behavior, and external interference. These dynamics can make it difficult to reproduce a problem consistently, hindering the troubleshooting process. Understanding these challenges and factors, technicians can better prepare for the complexities of troubleshooting network hardware. While the task might seem daunting, having an in-depth knowledge of potential hurdles and applying the appropriate troubleshooting techniques can lead to effective problem resolution. It's important for you to remember that troubleshooting is often a complex, iterative process. Patience and persistence are key. Activity: applying network troubleshooting techniques. Employability skills: analytical thinking, collaboration, and teaming. You've learned about different network troubleshooting techniques that IT support technicians use to diagnose and resolve network hardware issues. In this activity, you'll shadow Hector, a senior IT support technician, while you both apply troubleshooting techniques to network issues at your company. You'll answer questions during the process. You arrive at Hector's workspace and he shares that several departments in your company have reported inconsistent internet connectivity, slow network speeds, and frequent timeouts when trying to access shared drives. The company's IT ticketing system shows that the issues started a week ago and have been progressively getting more frequent. The accounting department is particularly affected, hampering their ability to finalize quarterly reports. The pressure is on to resolve this as quickly as possible. Man holding a laptop standing next to a server rack and holding onto a cable. Both of you begin troubleshooting the issues. You review the tickets and note the impacted departments, nature of the complaints, timeline of the issues. Hector reaches out to affected users and interviews them, asking targeted questions like, when did you first notice issues with internet connectivity and slow speed, to better understand the nature of the problem. Next, you and Hector head to the server room. Hector wants to rule out any physical issues by inspecting the network hardware components for visible damage or improper connections. While in the server room, Hector disconnects routers, switches, and repeaters, one at a time, and observes network behavior. You and Hector find a fraying Ethernet cable and a malfunctioning switch while in the server room. First, you replace the fraying cable. But you're unable to find any other external hardware damage or issues, such as overheating, physical damage, or an inconsistent power supply, on the malfunctioning switch. You and Hector decide to use another troubleshooting technique to identify why the switch is malfunctioning. Given that the switch is not malfunctioning because of external damage, Hector believes that the issue might be that the switch is improperly configured, or that the firmware is outdated. While inspecting the software, Hector notices that the switch is improperly configured. After addressing the configuration settings, Hector wants to understand the state of the network to see if the network continues to exhibit the problem or if the configuration changes solve the problem. He asks you to run a ping command to check if a host is reachable. Run a traceroute command to view the path the data packets take to identify any unusual detours that might cause slowdowns. While you're running the commands, Hector uses a network analyzer to capture and analyze network traffic in real time. This analysis allows him to detect specific inconsistencies or abnormalities in the data flow that might be responsible for the slow speed. Hector reviews the data from the diagnostics tools. There is an error message code that Hector doesn't recognize, and the data from the network analyzer indicates high CPU and memory usage on network devices. Hector decides to consult the documentation. After consulting documentation, Hector learns that the error message code is for CPU utilization threshold exceeded. This aligns with the high CPU usage indicated from the network analyzer data. Hector believes that the network issue the company is experiencing is due to resource overutilization. Hector decides to upgrade the malfunctioning switch and redistribute existing resources between the switches to balance the load more effectively. Congratulations! You've successfully applied network troubleshooting techniques to a network troubleshooting scenario alongside Hector. Together, you were able to use troubleshooting techniques to identify the cause of your company's network issues and resolve them. Preventative maintenance for network hardware. 2 male technicians checking hardware in a server room. Troubleshooting network hardware is not just about fixing problems as they occur, but also about maintaining the system to prevent future issues. Explore the following list to learn about best practices to achieve this objective. Update regularly. Ensure that you regularly update firmware and software. Most manufacturers provide clear instructions and tools to facilitate updates. Ventilate properly. Place network devices in well-ventilated areas to prevent overheating. Make sure there is enough space around devices for air circulation. Perform health checks. Perform routine inspections and monitoring to catch wear and tear or gradual decline in performance early. Keep documentation. Maintain detailed records of configurations, changes, and previous issues. Keep a logbook or digital record for your future reference. Use standard protocols. Follow industry standards and protocols for configuring and maintaining hardware. This ensures compatibility and security across the network. Train and educate. Continuously train and educate the users. Provide manuals, tutorials, or in-person training sessions to help keep their skills up to date. Seek additional help. Sometimes, complex problems might require additional expertise. Escalate to more senior team members or consult with specialists to help you find targeted solutions. In the complex and dynamic environment of network hardware maintenance, there is value in prevention. Preventative maintenance practices. Ensures the optimal functioning and security of the network. Mitigates the risk of serious and often costly breakdowns. Summary and looking ahead. In this lesson, you learned about network hardware issues and their symptoms. You learned about network troubleshooting techniques and even worked alongside an IT support technician in a scenario-based activity to apply the troubleshooting techniques. You're also aware of the preventative maintenance best practices to use for keeping a network at optimal performance. You've completed the final lesson of this module. Next, you'll review the module's key points and explore additional resources related to network hardware issues, symptoms, troubleshooting, and preventive maintenance. Points to remember. Key concepts. 1. Networking hardware is the set of physical components that enable and manage data transmission within and between networks, such as routers, switches, wireless access points, WAPs, network interface cards, NICs, repeaters, and bridges. 2. A computer network is a group of computing devices that share data and resources, such as the Internet, which is the world's largest wide area network, WAN. 3. A personal area network, PAN, is a network that connects devices over a small physical area, such as a room, using special device components and protocols such as Bluetooth and Near-Field Communication, NFC. 4. A local area network, LAN, is a network that connects devices within a specific location, such as an office building or a campus, using wireless or wired connections. 5. A wide area network, WAN, is a network that connects devices over a large geographic area, such as a city or a country, using fiber optic or copper cables. 6. A virtual private network, VPN, uses the Internet to create a secure tunnel between remote devices and a private network, allowing users to access resources as if they were physically connected. 7. Network cables, such as coaxial, Ethernet, fiber optic, and submarine communication cables transmit data across different distances and environments. 8. Network architecture is the design and structure of a network, including the physical and logical layout and the set of rules that determine how the network's components interact. 9. Placing network hardware involves assessing the network requirements, placing routers and switches, installing client-facing hardware, testing, documenting the installation, and providing maintenance and support. 10. Upgrading network hardware is a process that ensures the network functions efficiently and securely, aligns with organizational goals, and supports new technologies. 11. Upgrading network hardware involves assessing the current network, planning and preparing for the upgrade, implementing the upgrade, testing and verifying the installation, and maintaining the new hardware. 12. Being able to identify when network hardware is not functioning properly is vital. Common symptoms include slow internet speed, intermittent connection, or weak Wi-Fi signals. 13. IT support technicians use various techniques to diagnose and resolve network hardware problems, such as analyze symptoms, use diagnostic tools, inspect physical components, inspect software, isolate hardware components, monitor network performance, and consult documentation. 14. Effective and efficient network hardware troubleshooting requires following best practices such as understanding symptom overlap, consulting with documentation, isolating individual components, and using standard protocols. 15. Regular preventive maintenance helps in avoiding potential issues and ensures optimal network functioning. Practices for maintenance include regular updates, proper ventilation, regular health checks, documentation, training and education, and seeking additional help when needed. Big ideas. In addition, you explored or practiced these skills. Employability skills. Employability skills. Analytical thinking. Support a network engineer during the upgrade of a small company's network by choosing and placing network hardware. Apply network troubleshooting techniques, including, analyze symptoms, use diagnostic tools, inspect physical components, inspect software, isolate hardware components, monitor network performance, and consult documentation to a given scenario. Attention to detail. Differentiate between types of network cables such as coaxial, Ethernet, fiber optic, and submarine communication. Apply preventive measures, such as updating firmware, inspecting cables, and monitoring network health. Collaboration and teaming. Partner with an IT support technician to review a ticket, apply network troubleshooting techniques to resolve an issue. Problem solving. Recognize common issues with network devices, such as slow internet speed, intermittent connection, or security vulnerabilities. Align common issues with possible causes. Diagnose network problems. Learning objectives. Now that you've completed this module, you should be able to describe networking hardware components, types of networks, and types of network cables. Follow the process to place network hardware, network cables and connectors, and upgrade a network. Apply troubleshooting techniques for network hardware issues given a scenario. Explore more resources. To explore concepts covered in this module in more depth, check out these resources. What is networking? Opens in a new tab. This IBM website provides an overview of computer networks, including their types, components, protocols, purposes, and common terms and concepts related to computer networking. Introduction to LANs, WANs, and other kinds of area networks, opens in a new tab. This article by Bradley Mitchell for LifeWire provides an overview of the differences between LANs and WANs, and also identifies other types of networks. A Guide to Network Troubleshooting, opens in a new tab. This CompTIA guide provides an overview of the process and tools of network troubleshooting. Free ping tools for network troubleshooting, opens in a new tab. This guide by Bradley Mitchell for LifeWire provides an overview of free ping tools for desktops and mobile devices.